Hello my dear viewers. Welcome to a new episode. My dear lovely friend, focus in this episode, because we'll do something that you always ask for that he gave you once in the resistor episode, and we'll do it again now. Students, please lend me your ear. This is the electrochemistry chapter in 3rd secondary. I'll explain it for free. You can keep the lessons money for 6 PlayStation matches, and no hassle from the assistants, and you'll play me while you're eating on the dining table. Ready? Got your pen and paper? We'll study with El Dahi. Let's go. Among all the amazing inventions and technologies we make a day after the other, the battery still remains the hero invention, but a forgotten hero that's rarely talked about. Although without it, none of these new inventions would matter. The battery is the underdog of inventions, the victim of the spotlight of all the other technologies, despite being insanely important. No one asks about it. Can we get to the lesson, ABO Mead? The exam is in an hour. You're listening to me while you're on your way there? The story behind the battery, as we'll know today, starts in 1780 with the Italian scientist Luigi Galvani. He was in his lab like any scientist studying the frog's anatomy, and suddenly he noticed something strange when he touched the leg of the dead frog with an iron bar. The frog's legs moved. Since the frog was dead, Galvani's logical explanation for that was that animals had animal electricity that made them move even after they died. Sorry ABO Mead, what's animal electricity? This was just Galvani's explanation. He said it made the frog's legs move. Many scientists disagreed and didn't stay silent. The Italian physicist Alessandro Volta was reviewing his theory, and suggested another explanation that could be more logical. Volta thought that what moved the frog's leg was electricity, but had nothing to do with the frog, especially when Volta noticed that the bar Galvani used was iron, and the frog was on a copper slate. So it had nothing to do with the frog as much as electricity, copper, and iron. Indeed, Volta started thinking, how would he prove his idea? He designed the Volta battery. ABO Mead. The syllabus. This model consisted of zinc and silver discs alternating on top of one another with a salt-watered fabric between them, then again zinc and silver discs, and separate with salt-watered fabric. Then repeat, zinc, silver, salt-watered fabric, zinc, silver, salt-watered fabric, and so on. That way, Alessandro Volta invented the very first battery in history. This was enough to generate electricity. This battery was capable of generating direct current. Volta dumped Galvani's idea with frogs off the dumb ideas cliff. What Volta did wasn't just an invention where he proved that Galvani's theory on animal electricity was false, but it was a revolutionary invention that branched out a new science field, electrochemistry. Volta deserved the measuring unit of electricity to be named after him, volt. Is that it? ABO Mead. What does the battery have to do with electrochemistry? Or is it just a rhyme? My friend, don't underestimate electrochemistry. Without it, the world would stop. Countries would be head over toes for it. As much as it's serious and important, its main idea is very simple. Let us start with the name, electrochemistry. What does it mean? Simply, electrochemistry is the science that explains how can chemical reactions generate electricity, or how we can use electricity to create chemical reactions. Before diving into it, let's take a step back and ask, what's electricity? Electricity is the movement of electric charges. When you find an electric charge moving, then this is electricity, which are usually electrons. Any electrons hanging out is electricity. This means that electrochemistry includes the movement of electrons. This movement is caused by chemical reactions. The chemical reaction that creates this electricity is known as oxidation and reduction reactions. Oxidation is the process of losing electrons from atoms or particles. When the particle or atom loses an electron, that's oxidation. The other one, reduction, is its opposite. It's when the atom or particle gains an electron. Again, oxidation is losing electrons while reduction is gaining electrons. Of course you noticed that an electron is lost from here and goes there, and we said that when an electron takes friends to hang out, its electricity. An example. It'll be in the exam. ABO Mead? I'm not a question bank, my friend. Let's take the iron atom as an example. This atom in its normal state has 26 electrons, and since it also has 26 protons, then it doesn't have a charge. The number of positive protons is equal to that of negative electrons, so it has neutral charge. For any reason, this iron atom was in a busy bus and got pickpocketed and lost 2 electrons. So instead of having 26 electrons, it now has only 24. What happened here? Tell me, it's oxidation. Good boy, I said it, but okay. When this happens, the iron atom turns into iron ion, This iron ion is same as iron atom but with 24 electrons instead of 26. The iron atom turns from a neutral zero-charged atom due to having 26 positive and 26 negative charges, into an iron ion that's missing 2 electrons, leaving the ion charged with 2+. This is an oxidation process. We can use the following chemical equation to describe the oxidation process. It simply says that the iron atom turned into an iron atom with 2+ charge plus the 2 electrons that were released. Now the reduction process is the total opposite. Take the chlorine atom for example. This atom has 17 electrons and 17 protons in its normal state. 17 with 17 is also neutral, an atom without charge. The chlorine atom is zero charged, and for some reason, this chlorine atom gained an electron, so instead of having 17 electrons it now has 18. So the chlorine atom turns into a chlorine ion. Anything that its charge changes turns into an ion, whether positive or negative. Again, the chlorine ion is the same as the chlorine atom but here with 18 electrons instead of 17. The chlorine atom turns from a zero-charged atom into a chlorine ion with -1 charge. What happened to the chlorine ion as reduction process? We can use the following chemical equation to describe the process. It says that chlorine atom turned into a chlorine ion of a -1 charge after gaining an electron. The main idea here, my friend, is that we found out there are elements with an ability greater than others to lose electrons, like you with losing your keys. They keep losing electrons, too. Or in other words, some elements tend to be oxidized easier than others. The idea here is that we found chemical elements that love oxidation. They tend to be oxidized, they're easy to be oxidized and lose electrons. They keep releasing electrons. And vice versa. There are elements with more tendency towards reduction. Like you. ABO Mead? I'm not explaining anything. I won't. What do you mean, like you? ABO Mead? I won't explain it, and it'll be in the exam. Fine, I'll continue. Just for all the students working all year. There are elements that tend to be oxidized and others tend to be reduced. Chemists were able to arrange the elements we know according to their tendency to gain or lose electrons. They called this arrangement electromotive series. When you go up in the series, you find elements tending to gain electrons more, or in other words, as you go up the series the elements tend to be reduced, and we call them strong oxidizing agents. You're confused now, right? The elements that tend to be reduced are oxidizing agents? And strong too? I'm confused. ABO Mead. Logically, my friend, focus. You have an element that keeps releasing electrons, and letting them go. That's an oxidized element. The ED is for being an object. These electrons go to another element that's being reduced, which is considered to be an oxidizing agent. If it's reduced, then it's oxidizing. In short, the object here is the subject there, and the subject here is the object there. Get it? So the oxidizing agent is reduced, and the reducing agent is oxidized. You'll get it, don't worry. Any subject is an object and any object is a subject. What brought grammar here? ABO Mead. Zinc, for example, is higher than copper in the series, which means that zinc has higher tendency to lose electrons, or chemically, the zinc is a stronger reducing agent than copper. This means that if we got a zinc atom next to a copper ion, the zinc atom will be oxidized, losing 2 electrons to the copper ion, so the zinc turns from a zero-charge atom to a zinc ion with +2 charge. Here, the one losing electrons becomes the positive. I know it's confusing, but guess what? Life. On the other side, the copper ion that gained 2 electrons from zinc would turn into a zero-charge copper atom. Why? Because the copper ion is missing 2 electrons to reach zero charge. The first equation of zinc is an oxidation process, while the other one for the copper is reduction. Good, great? You feel like you're getting it? Wait, there are 3 more points and then we dive into the real thing. ABO Mead, I want to switch major. I'm afraid it's a bit late, my friend, maybe next year. Attend the exam and we'll see how it goes. Firstly, that the oxidation and reduction processes always happen together. When you see something being oxidized, know another is being reduced. And when I see something being reduced, then know another is being oxidized. Now stick to your major, excellent. That's why instead of saying oxidation-reduction reaction, we can just say redox reaction. Just redox reaction, all mushed together. Secondly, and keep it in mind, that the physical properties of these elements change according to whether it's a neutral charged atom or an ion with a charge, positive or negative. For example, the zinc atom. In its normal state it has zero charge, the positive equals negative, no charge. In that form, it's in a solid state, that's its physical property, it's solid. Whereas the zinc ion, the zinc atom, after losing 2e now has a +2 charge, because what loses electrons becomes positive. Apparently, loss is a win in chemistry. When you examine the zinc ion physical property, it won't be solid state. So 2 electrons, ABO Mead, can do this to zinc? 2 electrons can make the zinc solid, and not having them makes the zinc not solid? And I ask myself why I'm missing electrons. What are you saying, my friend? I just don't feel fine. ABO Mead. My friend, please hold on to your solid state, and try to keep your electrons as much as you can, and please don't concede to anyone with heat and change your state. What I want to say is when zinc is in its normal state and electrons, it's solid. When it loses 2 electrons and has +2 charge, it turns into aqueous state, it's dissolved in water. Thirdly, and keep it in mind. And not keep in mind the rest? No, keep everything in mind, my friend. The processes of oxidation and reduction between the elements occur naturally and spontaneously in nature. As long as nature is still active, there's always oxidation and reduction, but on one condition: to have at least one of the elements tends to be either more oxidized or reduced than the other. This natural oxidation and reduction process can be called as galvanic cell. It's important, and named after the scientist Galvani, the first one we talked about, the frog one, you know. It's true, Galvani said some weird stuff about animal electricity, but he was a scientist and tried to explain and bring any contributions to science. Remember these 3 notes well, because they'll help us later on with the battery. Wow, ABO Mead, I almost forgot the topic of the episode. I want to say, ABO Mead, that I'm under the covers now. Get out. I don't like jokes in my class. We aren't here to make girls laugh, only I can do that here. Like we said, the battery depends on chemical reactions between elements, and these chemical reactions result in electricity. One of the earliest simple and successful batteries in creating electricity was designed and made by the English chemist John Daniell in 1836. It was later on known as the Daniell cell. Let me tell you the recipe to the Daniell cell. It's done in 1 cooking pot, less hassle, and happy guests. We'll need 2 beakers, these glass cups in the lab. We will fill both beakers with water. In the first beaker we'll put zinc sulfate, and in the other beaker, we'll put copper sulfate. Ingredients in all households. We'll stir the beaker well until the salts are dissolved. After the salts dissolve, we'll take a zinc piece and put it with the zinc sulfate, and take a copper piece and put it in the beaker with copper sulfate. Chemists don't say piece though, they say electrodes. But it's still a piece of metal. We'll call them electrodes. Anyway, we'll connect the electrodes together with a wire, connect the zinc to copper. Suddenly an electric current passes through the wire. That's all. ABO Mead? Yes, my friend, that's the battery. Did we operate it yet, ABO Mead? No, I meant the explanation. Wait, ABO Mead, you want me to believe that if I got a light bulb and connected it to the wire connecting the pieces that you call electrodes with your chemist friends, the light bulb will light up? Why the tone? Yes, it'll light up. Really, ABO Mead? Yes. So we generated electricity? My friend, didn't we say battery means electricity? The battery's only job is to give you electricity. That's all, ABO Mead? That's all. This is one of humanity's greatest achievements. All what I'm saying is one of humanity's greatest achievements. Can you elaborate, ABO Mead? I don't understand. I'll tell you, my friend, how we generated electricity from these salts, and the 2 metal pieces connected with a wire. Let's go back to the beginning, when we dissolved the zinc sulfate and copper sulfate in water. Each solution had free ions. The first beaker has zinc ions and sulfate ions, while the second beaker has copper ions and sulfate ions. When we dipped in each beaker respectively the zinc and copper electrodes and connected these electrodes together, some kind of competition starts between zinc and copper over electrons. I wonder who will win. Remember the very important table I told you it'll be in the exam? The electromotive series, remember? If we looked at this table, we'd find zinc is higher than copper. Excellent. And what does this mean? That zinc has more tendency to lose electrons. Keep in mind, my friend, a higher tendency than copper. Always say higher than, there's no absolute higher. A thing to note here, the question can be asked backwards. How? I'm nervous now. Isn't copper below zinc in the table? This means that it has higher tendency than zinc in gaining electrons. You have one that wants to lose electrons and another wants to gain them. What a great fix-up. Now, what happens inside the small battery we made, is that when we connect the zinc and copper electrodes, the zinc ions of the zinc electrode dipped in the zinc sulfate solution somehow feel the copper ions in the other beaker. How, ABO Mead? telepathic? No, my friend, they're connected with a wire. On the other side, the copper ions in the copper sulfate solution also feel the zinc ions over there. Like we said, some want to give electrons and others want to take. These want to give electrons while those want to take electrons. So the zinc ions finally start to drop and lose the electrons, and that way what process starts? You focused? Oxidation process. Zinc is being oxidized. Chemists love to label everything, and humans too. They called the area that experiences loss of electrons with the zinc electrode as anode. Like we said, every zinc atom loses 2 electrons, and these 2 electrons move in the wire with their mates to the other beaker. And here 2 important things happen at the same time in each beaker. The beaker with the zinc, once the atom loses 2e, it turns from 0 charged and from being a solid metal, into being a zinc ion with +2 charge, based on the equation we explained before. Zinc here starts to dissolve in the solution, and leaves behind the zinc electrode. The zinc ions move away from it. I am now an ion, I'm different, I'll swim with sulfate solution. Leave your electrons first, then join me. The 2 electrons dumped from the zinc atom move through the wire until they reach the copper electrode in the other beaker. Once the copper ions in the copper sulfate solution feel the electrons arriving in the copper electrode, they start moving towards it. The electrons are negative and they're positive, so an attraction starts to happen. Until one of these ions reaches the surface of the electrode and gains the E. What happens then, my friend? Reduction. ABO Mead. Excellent, my friend. Chemists decided to label where reduction gaining electrons occurs as cathode. That way, copper ions turn from being dissolved in the solution to a 0-charged copper atom that's attached to the copper electrode where it gained the electrons. All this drama is because a zinc atom lost 2 electrons and sent them through the wire to the copper ions. Thank you. Of course, my friend, we have lots and lots of zinc atoms, and also lots and lots of copper ions, so a trend starts among atoms where they send their electrons to the other side. Here an electron. Grab an electron, catch 2 electrons. All the zinc keeps sending through, and the copper keeps receiving and gaining, and everything. Give us the electrons. Notice something? There are electrons moving, there's electricity, you now have a battery, and when does it expire? When does your phone power off? When does your electric Tesla stops? When all the zinc atoms turn into positive zinc ions. That means that the battery is dead. When someone tells you the phone battery or any battery is dead, no matter what the elements are, this means that the one sending electrons is done. There are no more electrons to send. If we left these processes happening, we'll notice changes in the beaker's electrodes. You'll see one getting smaller and one getting bigger. The anode is always getting smaller, and the cathode is always getting bigger. As long as the zinc atoms release electrons, it gets dissolved, so the solid zinc mass starts shrinking, and vice versa with the copper. The copper ions that leave the solution and get attached to the copper electrode, you'll see that by time the copper electrode is getting bigger, copper keeps precipitating. With all due respect to the explanation, I got it and hope I'd ace the exam. But what if I saw a question that says, calculate the electromotive force, EMF, for this galvanic cell? Do I leave the question empty? No, wait. This question simply asks how much electricity is generated. Even more simply, how much voltage does your battery have? To calculate the electromotive force, we use something called reduction potential, where the EMF of the cell equals the reduction potential of the cathode minus the reduction potential at the anode. The reduction potential is a fixed lab measured value for most elements. Scientists already calculated it. If you looked at the electromotive series table, you'll see these values. It's already calculated. In our case, copper's reduction potential is the cathode's reduction potential, which is 0.34 volt, while the reduction potential of zinc is the same as anode, which is minus 0.76 volt. When you put these values in the equation, congrats, you got it. So this cell all in all generates 1.10 volts. If we used other elements, it will generate different volts. Pay attention here because it's important. That's to make a super battery. The bigger difference there is between the elements in their reduction potential, the bigger the EMF value of this cell is. Meaning, if you looked at the top element in the table and paired it with the last element in the table, theoretically, if you used them as electrodes with sulfate solution, they will theoretically make a battery generating highest voltage. See how easy and nice chemistry is, my friend. We now formed an idea about what happens with metals and solutions to generate our lovely electricity. Let me tell you that just as there are reducing elements in nature, there's also reducing people. Who are they? ABO Mead, so we can beat them up. It's me, my friend. I reduced the lesson. There's an important and last part that I reduced. I reduced what's known as the salt bridge, also known as ion bridge. Without this salt bridge, the battery won't work. If we took a step back and remembered the dissolved ions in each beaker, before dipping the metal electrodes, we'll see that each beaker has positive and negative ions. The positive zinc ions and the negative sulfate ions are in a beaker. The other beaker has positive copper ions and negative sulfate ions. In each beaker, we'll mostly find the amount of positive charges equals the amount of negative charges. But when the oxidation and reduction processes start, the percentages of dissolved charges in every solution change. If we looked at the zinc, we'll see that by time there are new positive zinc ions dissolving in the solution, the ones that lost electrons, and there are no negative sulfate ions for them. So now you have an oversupply of zinc ions that created a beaker filled with positive charges. There are no negatives to balance them out. The existing sulfate already has its zinc. The new zinc ions have nothing to balance with. So it made a beaker of positive charges. On the other side, as the positive copper ions leave the solution because there are electrons coming and these ions want electrons, so they went to receive them. The ions left the solution of negative sulfate ions, so the beaker is now filled with negative charges. So now we have a positive beaker and a negative beaker. The positive, plus Va, beaker is positive as new plus Va zinc ions dissolve in the solution, while the other beaker is negative because copper ions left the solution. You're wondering, my friend, why am I telling you this story? My friend, we want our battery to work, and this isn't good for our battery. Because by time, if these charges kept piling up like this, the battery will die, it won't generate any electricity. You have two beakers, my friend, one with positive charge and one negative, and the electrons are already negative, so when one keeps being negative, electrons will stay away from it because negatives pull away and would want to move to the positive beaker, so the battery stops. The electrons aren't moving, there's no electricity. Here, we use the salt bridge to solve this issue. The salt bridge is a U-shaped glass tube that we fill with a solution that doesn't react with the beaker's ions like the zinc, copper, and sulfate ions, nor with the metal electrodes, the zinc and copper. ABO mead, if it doesn't react with all this, then why use it? Isn't there enough elements? The salt bridge's main usage is to balance out the charges that can be precipitated in the solutions. For example, if we filled the tube with salt solution, sodium chloride, when it's dissolved in water, the salt breaks into positive sodium, Na, ions and negative chloride, Cl, ions. The use of these ions is to move freely between the beakers through the bridge, so these positive Na ions move through the salt bridge towards the beaker with negative charge. The copper beaker and balance out the charge. ABO mead, why do the sodium ions go to the sulfate ions? Isn't one positive and one negative? And positive loves negative? Let them be. Same thing happens with the negative chloride ions, they move through the salt bridge towards the beaker with positive charge and balances the charge. It's not necessary to use sodium chloride, we can use potassium chloride, KCl, or sodium sulfate, Na2SO4. The important thing is to be a neutral compound that won't react with anything. It just balances out the charges without a hassle. As much as batteries are an amazing and genius invention, the basics they operate by haven't changed since Volta's time. Since the 18th century, they're metal electrodes with difference in EMF, where one wants to give electrons and the other wants to gain electrons. These electrodes are dipped in electrolyte solutions, which is defined as a solution that allows free movement of electrons. Then we connected the electrodes in a specific way together, and you then find a flow of electrons, or also known as electricity. The shape of batteries has been through many changes. For example, instead of copper electrode, we can use mercury, and put it with zinc in potassium hydroxide, Co, solution, and create mercury batteries that we use in headphones, watches, and cameras. Or we can use lead, Pb, and lead dioxide, PbO2, in sulfuric acid solution, H2SO4, creating the car's battery, that doesn't only generate electricity to move the car, but it also can be recharged after it expires and reuse it. Or we can use the highest metal in the electromotive series, lithium, Li, to create the lithium-ion battery, which is extremely important. This type of battery could be the strongest one ever till now, because it can store a huge amount of energy in a compact size, and has a long lifespan where it can be recharged a lot without low performing. It is also lightweight compared to other types. This all makes it ideal to be used in laptop and mobile phones batteries. All these qualities created a competitive market for it, where its value reached $66 billion in 2021, and is expected to reach over $274 billion in 2030. These numbers are expected to increase in an unprecedented way, especially with the continuing evolution and expansion in producing electric cars, like Tesla, Lucid, Rivian, and the BYD in all the electric cars. By the way, BYD is one of the largest battery manufacturing factories worldwide. That's BYD, it's a dangerous and very important company. Remember this company, my friend, for the future. Other than the fact that BYD is the most famous Uber car in Egypt, order an Uber and you'll most probably get a BYD. But apart from the future and Uber, if we took a step back and remembered the early 20th century, we'll see that batteries played a pivotal role in the development of transportation and electrical systems that reformed the entire modern world, but they're still underestimated and often ignored. Although batteries back in the day stored way less energy than now, and also had less performance and quality than nowadays, it was an essential element in inventions that changed the world. For example, the surprise that in the early 20th century, electric cars existed already in France, Germany, and the UK. Before Elon Musk, ABO Mead? Yes, before Elon Musk. 100 years before Elon Musk. You'd ride the electric car with your friends with all pride, and can drive for 120 kilometers with one charge. Its speed reached 30 kilometers per hour. We're talking about late 19th and early 20th centuries, these numbers were above and beyond. But unfortunately, no one thinks about the battery. No one thinks about its importance in operating old telephone and telegraph systems and their use in electricity stations to generate stable electricity. My friend, I just found the battery dead, so I thought I'd revive it. That's all. Today's lesson is over. Go home, study well, solve many mock exams, the 2008 final, the 2013 final, the Sudan finals too. That's all. Study well and read the newspaper's question bank. That's all. What else? Don't forget to pay outside with the assistant. I thought it was free, ABO Mead. Nothing is free. There's no free lunch. I don't carry change, my friend. I want holes, give me 200 bills. Last but not least, don't forget to watch the old episodes and the new ones, look at the sources and subscribe if we're on YouTube. One last thing. I want you to pick the hardest topic in your syllabus. Write it in the comments, and the most comments with likes. I'll think about it. Maybe I'll make an episode on it. I liked the whole explanation thing. I'll skedaddle now. Bye, my friend.